to have a function divided by another function. And then you not only have to have that, but you have to check and make sure that if you have a function divided by a function, you're going to get your basic indeterminate form, 0 over 0. So remember, we had to always check those and make sure. Or you can get infinity over infinity. That will also work for L'Hopital's rule. So one of the biggest things about L'Hopital's rule is you need to check first and make sure you're allowed to use it. Because if you don't have a 0 over 0 problem, or if you don't have infinity over infinity, you can't use L'Hopital's rule. Okay, so that's the first thing. You got to check those. Once you decide, I do have that, and I do have this quotient form, then all L'Hopital's rule says is that the limit of your original problem of that quotient will be the same thing as the limit of the derivative of the top and the derivative of the bottom. So it makes it a lot easier because then you're just looking at the individual functions. You don't have to do any quotient rules or anything like that. You just take the derivative of the top, take the derivative of the bottom, and then find the limit of that. Okay, so it's a pretty straightforward, easy process. Now here's the thing. Typically, we're going to start off, and if you did the video problems, you find the limit, you do the derivatives, you get your answer. Well, sometimes when you take the derivative and do L'Hopital's rule and you plug in numbers, you still get that indeterminate form. So every now and then you have to do this process more than one time. And when you do that, my biggest thing to you guys is always simplify before you move on. So anytime you've done your work, make sure you simplify it before you go to the next step. It makes it a little bit easier. Okay? All right, so that's where we're going to start, the basic ones, and then we're going to look at some crazy ones in a little while. All right, so I'm going to start with number 6 with you. Put this back over here. All right. Okay, so first and foremost, you're going to check these. So if I look at number 6, I know that's a limit problem. It's just a quotient. First rule of thumb, always plug it in and see what you get. So if I plug in -2 into the numerator, -2 squared is +4. 4 minus 4 is 0. I always do my check over here on the left because I don't want to do the work on the right. So I have 0 in the top and then -2 plus 2 in the bottom. So I get 0 over 0, which means I could factor this or simplify it, do it the way we did in chapter 1. So I could factor. X squared minus 4 would be x plus 2, x minus 2, right? I cancel out the x plus 2s, and I would plug in my number there. And that's still fine. You can always do your problems that way. So what we're learning today is just a different way to go about this. So I see 0 over 0. Now I'm thinking, oh, I have this new rule. Okay, so what we want to do, anytime you use L'Hopital's rule, you have to write that you're using that, and so we use a little LH above the equal sign. You only do that when you're going from the function to its derivative. If you're simplifying, you don't have to write the LH over the equal sign. So this is just saying that we're using a specific rule, because otherwise you can't set these things equal to one another. It wouldn't make sense to do that. So we're going to use L'Hopital's rule, take the limit as x approaches -2, and then the derivative of the top divided by the derivative of the bottom. So the derivative of x squared is 2x. Derivative of -4 is 0. And then the derivative in the bottom, derivative of x is 1. Derivative of 2 is 0. All right, so there's your new problem, and now you're going to plug -2 into this. Okay? And here's where I'm saying if you can simplify it first, simplify it before you do any solving. 2x over 1 is just 2x, so we don't have to simplify that much. So we're going to plug in -2. So 2 times -2 is -4. So there's your limit, and you would have got the same answer if you factored it, the way we did in chapter 1. So it's just another way to solve these things. Okay, so same thing with number 7. Almost the exact same problem. So I could factor that, and I could do it that way. But again, I'm going to check. The limit as x goes to -3. Plug in -3, so we get 9 minus 9, so that's 0. And -3 plus 3 in the bottom is 0. So please check these, because there's 2 of them in this problem set where you can't use L'Hopital's rule. I'm pretty sure there's 1 or 2 in WebWorks where you can't use L'Hopital's rule. So they want to make sure that you're looking at the fact that you do have this indeterminate form. All right, so since I have it, I'm going to do my derivatives, L'Hopital's rule. Limit as x approaches -3. So the derivative of the top is 2x. Derivative of the bottom is 1 again. So now we can plug in -3 into our limit problem, and we end up with -6. Okay? So for a lot of you, you like this better, because you're either maybe not so good at factoring or whatever, but it's just another method to do it. All right, number 8. Let's put 1 in there. So the natural log of 1 in the top is 0, and 1 minus 1 in the bottom is 0. Okay, so there's an indeterminate form. So this would be one where you'd want to do L'Hopital's rule. You can't do anything much with natural log otherwise. All right, so we're going to look at the limit as x goes to 1 and take the derivative of the top, derivative of the bottom. So the derivative of natural log, 1 over x, and the derivative of x minus 1 is just 1. So we have 1 over x, and we're going to plug 1 into that. 1 over 1 is 1, and so there's your limit. Okay? All right, number 9. Plug it in and see before you start doing derivatives. This is the first one where we can't use L'Hopital's rule. So if I check this, and I'm just going to check it here because I'm not going to get 0 over 0, and I know that already. So if I plug in 0 and I do the sine of 0 over 1 plus the cosine of 0, the sine of 0 is 0, but the cosine of 0 is 1. So in the bottom, you get 1 plus 1. You get 0 over 2. So that's just a direct substitution problem. 0 over 2 is 0. That's your limit. So there is no L'Hopital's rule. I can't do a derivative. I would get the wrong answer if I tried to do L'Hopital's rule on that problem. So over here, I'm going to write L'Hopital's rule is not applicable. Okay. That one was special because I didn't get 0 over 0 or infinity over infinity. So you have to check these. All right, so the next page are the rest of these basic ones, but they have little twists to them, like constants in them or other things. So look at those. And then there's one on this page that also is not L'Hopital's rule. So we have to keep checking as we go through. All right, we okay so far? All right. All right, so number 10. This one has some constants in it, and this is a good one because as I've been checking some of your tests, some of us, again, still don't remember how to find derivatives of exponential functions. I'd take off a few points on those as I was going through. All right, so let's check. First off, direct substitution. So x is going to 0. So a to the 0 is 1, minus 5 to the 0 is 1. So we get 1 minus 1 in the top, so that's 0. And obviously in the bottom, 9 times 0, 0. So this is an indeterminate form, so I can use L'Hopital's rule. Okay, so the limit as x goes to 0. All right, so good review. So remember, a is a constant, just like 5 is a constant. So this is an exponential function. Derivative of any exponential function is the exponential function times the natural log of the base. So the derivative of a to the x is a to the x times the natural log of a. That's its base. Okay, minus the derivative of 5 to the x is 5 to the x times the natural log of its base, which is 5. Okay, so that's the derivative of the top. This is straight from WebWorks. I remember this problem. And then in the bottom, derivative of 9x is 9. Now remember, a is a constant. You're substituting in 0 for x, not for a. So you're allowed to have a's in your answer. It's a constant kind of problem. All right, so now if we let x go to 0, okay? So if we're now substituting in, I'm going to do a to the 0. I'll go and write it out. You can do it in your head if you want, but this is what I have. So a to the 0 times the natural log of a minus 5 to the 0, natural log of 5, over 9. So the a to the 0 is 1, and 5 to the 0 is 1. So I end up with the natural log of a minus the natural log of 5 over 9. And that's your answer. Can't do anything else with it because I got that constant in there. That's how I would type it into WebWorks. Remember, A, B's, and C's in WebWorks are constants. So that's okay to have those in your answer for some of these. All right, good. Okay, number 11. It's the first one, I believe, where we have to do L'Hopital's rule twice. So let's look at how that works. All right, so let's check first. We got x going to 0. So 1 plus 0 is 1 minus e to the 0. Well, e to the 0 is 1. So we end up with 1 minus 1 in the top, so we get 0. And obviously the bottom, 3 times 0 squared, that's 0. Okay. All right, so we can do L'Hopital's rule. So the limit as x goes to 0. And by the way, I'll say this again, some of you are walking in late, but when you use L'Hopital's rule, the only reason this is equal to this, I got an equal sign there, is because I'm using this theorem. Okay, L'Hopital's rule is a theorem. So I put it there because otherwise these two things are not equal to one another. Okay? But it's the only place that you have to write L'Hopital's rule. So when you're doing these steps, that's where you put it. That shows that this and here are derivatives of one another. And then notice from there on out, I'm just doing equals, because then I'm just simplifying, okay? So you only put the LH, you don't put it on every single equal sign through the problem. You're only doing it on that one step where you're taking the derivative. Okay, all right, so derivative of the numerator. Okay, derivative of 1, 0, derivative of x is 1, and the derivative of e to the x is e to the x. So 1 minus e to the x is the derivative of the numerator. Bottom derivative is 6x. All right. So now, there's my derivative. So now I'm supposed to put 0 in and get my answer. But if I put 0 in, I get 1 minus e to the 0 over 6 times 0. So that's 1 minus 1 over 0. I still get 0 over 0. Okay. So what that tells you is that this limit problem is still indeterminate, which means you can do L'Hopital's rule on this again. So now we're going to take this problem, and I'm going to write it down here. So I'm going to kind of start a new problem. So now I have this, and I need to take the derivative of that. Since I got 0 over 0, that means I can keep going. There's an answer somewhere. Okay, so now I'm going to put equals with the LH on top of it to show that I'm going to do another derivative. All right, so take the derivative of this problem. So the derivative of 1 is 0, derivative of negative e to the x, negative e to the x, and then the derivative of 6x is 6. All right, so there's a new problem. I'm going to substitute 0 into that. So now I get negative e to the 0 over 6. E to the 0 is 1, so that's negative 1, 6. That time I did get an answer. So there's your limit. Okay. So every now and then you'll have to do L'Hopital's rule more than once, but you always check. Always plug in your number, always see what you get. And if you still have that 0 over 0, we haven't done any with infinity over infinity yet. I think it's coming, but still, you remember, for L'Hopital's rule, you can get 0 over 0 or infinity over infinity. Back in chapter 1, we could only get 0 over 0 to do the factoring and that kind of thing. All right, so most of these end up being 0 over 0. Every now and then we'll get a different one. So, okay, 12 is just like 11, except we have an A. So we have constants, which means probably I might have an A in my answer. Not sure yet, but we'll see what happens. Might go away, I don't know. All right, so let's check. X is going to 0. So e to the a times 0 would be e to the 0, which is 1. So 1 minus 1 is 0 in the top. And obviously 0 to the 7th is 0. So we're ready to do L'Hopital's. Start an equal sign there for that one. Okay. So limit as x goes to 0. All right, so let's look at the top. So the derivative of 1 is 0. What's the derivative of negative e to the ax? It would be negative e to the ax times the derivative of the exponent, which would be a, right? Derivative of ax would be a. So negative e to the ax times a over 7 x to the 6th. Okay. All right, so if we plug in 0, what's going to happen? If we plug in 0, we're going to get negative e a times 0 times a over 7 times 0 to the 6th. All right, so right here we have negative e to the a times 0. So that's negative e to the 0, which is negative 1 times a over 0. Okay, so that gives you negative a divided by 0. So a negative number divided by 0. What does that tell you about limits? When you get a number divided by 0? Those are asymptotes. So it's either plus or minus infinity. So if it's a negative number, that's obviously going to negative infinity. Okay, so remember, when you have a number divided by 0, your answers are either plus or minus infinity. So this one kind of helps us because we have the sign there, so negative. And you could graph it. I mean, you could plug in a number for a, I guess. Okay, so you get negative infinity. All right, 13, trig problem. So remember we're doing 0. So the ordered pair at 0 is 1, 0. So sines at 0 are 0, and the cosines at 0 are 1. So if I look at this and just plug in 0, 10 times 0 is 0. So the sine of 0 is 0 on the top. And if you plug in the bottom 0, doesn't matter, that's b. b times 0 is still 0. So the sine of 0 on the bottom is 0. So when I do L'Hopital's rule and I end up with cosines at 0 are going to be 1, so I'll be able to work those out. All right, so L'Hopital's rule. Limit as x goes to 0. All right, so the derivative of, this is a chain rule, so don't forget to do the derivative of the inside. So the derivative of sine is cosine, leave the inside alone. And then times the derivative of the inside, which is 10. And then the same thing on the bottom. Derivative of the sine of bx is the cosine of bx, leave the inside alone. And then times the derivative of the inside, which will be b. All right, so now you're going to plug in 0. So we're going to do the cosine 10 times 0 times 10. And then the cosine of b times 0 times 10. Oh, times b. Oops. All right. All right, so that's going to end up giving you 10 times 0, 0, b times 0, 0. So we'll have the cosine of 0 times 10 in the top, and the cosine of 0 times b in the bottom. And the cosines of 0 are 1. So we get 1 times 10 over 1 times b. So that is 10 over b. So again, I had b in my problem, it's going to be in my answer. Strange looking, but that's what it is. Okay? All right, number 14, check it. The natural log of x, and x is going to 0 from the right. It's going to 0 from the right because 0 is an asymptote of the natural log. Okay, so remember what the natural log looks like? It goes through 1, 0, and it looks like that. So you kind of have to keep the exponential function in your head and logs in your head so you kind of remember what those graphs look like. All right, so as we approach 0 from the right, if we're plugging this in, direct substitution, we get negative infinity in the top. And if we plug in 0 in the bottom, or really close to 0, we're going to get 0 in the bottom. So that's not in determinant form. Again, that's an asymptote, a really large negative number over 0. So that's negative infinity. Okay? Numbers divided by 0 are asymptotes. You could always graph these. A lot of these are on the calculator part of your test, so you can use your calculator. But that one you can't use. So again, L'Hopital's rule, not applicable. Okay, we did not get 0 over 0 or infinity over infinity. Okay, so that's the end of the regular ones, okay? All right, so the next couple of pages, we're going to use some different tricks so that we can use L'Hopital's rule. Because you can see L'Hopital's rule is pretty nice. Get derivatives, makes the problem easier. So let's look at the ones coming up then. Got a lot of pages for just a few more problems. All right. So the first type we're going to look at, before we look at the top, look at 15, 16, and 17. These are multiplication problems. So right now, given a multiplication problem, I can't use L'Hopital's rule. But the nice thing about multiplying is you can change it into a division problem very easily, okay? All right, so that's what we're going to look at up at the top. So we need to make these product problems into division. Okay, well, if I need to have a function divided by another function, and I have a function times a function, then if I take one of these two functions, okay, and put it in the denominator as 1 divided by that function, that's the same problem, right? 1 divided by something is the same thing as that function if I'm moving it from top to bottom. Okay, think about, x to the -3. It's the same thing as 1 over x cubed, right? So I can move things by taking and flipping them. So that's kind of what this is telling you on the top. So you're going to pick either one of the functions and put it in the denominator by doing 1 over that function. And I'm going to do that with you for the first few problems, but usually then you're going to simplify it, okay? But I want you to see that we are doing this. So notice you can do either function and put it in the bottom. I always tell you to try to take the easiest problem and put it in the bottom, what looks easier, because that's going to make the problem easier for you. And I'm going to also write never put the ln in the bottom. Natural logs, because you're going to be in a vicious cycle and you'll never get an answer. So try to remember not to put natural logs in the bottom. All right. So if I have a product, then you're not going to check for 0 times 0. Okay. Remember, you checked for the indeterminate form 0 over 0. So if it's a product, you want to check for 0 times infinity, okay? Okay. So if you get 0 times infinity, and then you take the infinity part, whatever that function is, and write it as 1 over that problem in the bottom, that changes to 0, right? Because if you have infinity on, think about it, if you got a really big number, 1 billion, and then I write 1 over 1 billion, that changes it. Instead of being infinity, it's getting closer to 0, right? So that's why we do that. So you're looking for this combination. That's going to help you get the L'Hopital's rule form. All right, so let's go to number 15. Neither of these are easy, although some of you might say sine is easier, but I'm actually going to put the cotangent in the bottom because cotangent has a reciprocal, so we're going to use that one. Okay, so what I'm going to do is start off by rewriting this as the limit as x goes to 0. Oh, and I didn't check first, so let me check. Okay. All right, so plugging in 0. So I got to make sure I get 0 times infinity, or infinity times 0. Cotangents, asymptotes. I just taught my pre-calc classes, so I want to remind you. Cotangent and cosecant have asymptotes at 0. Tangent and secants have asymptotes at pi over 2. Okay, so I just taught my pre-calc kids this, that the word cotangent and cosecant both have the letter O's in them. So that's how I remember that those have the asymptotes at 0. 0 is like that O in the word, okay? So cotangent and cosecant, even though cosecant is CSC, I understand the shortcut, but the word cosecant has an O in it. Those have asymptotes at 0. So if this has an asymptote at 0, cotangent of 0, that would be infinity. Okay, and then the sine of 0, we already know that. Sines of zeros are zeros. So that gives me that form that I need. Okay. So if you're doing a tangent or secant problem, those would probably go to pi over 2, because pi over 2 is asymptotes for tangents and secants. Okay? All right, so I'm going to take cotangent and put it in the bottom. So I'm going to write the sine of 6x, leave that, and then divided by 1 over the cotangent of 2x. It's the same exact thing as what we have up at the top. Okay. You divide by the reciprocal, that's what you get. All right, so that's the step. So now I have a division problem. And then typically you're going to take the bottom and simplify it. So what else can I do instead of doing 1 over cotangent? What is that, the same thing?
Tangent.
That's tangent, right? So let's rewrite this. Because remember, you're getting ready to do derivatives, and I don't want to do a derivative of a fraction if I can help it. So the sine of 6x over the tangent of 2x. 1 over the cotangent is tangent. Now I'm ready to do L'Hopital's rule. And I don't have to check. The nice thing about this, as long as you check it at the beginning, you don't have to check here, because now you're going to have 0 over 0. Okay, but because we already checked it, I don't have to check it again. All right, so now I have my quotient. Now I'm going to do my L'Hopital rule part, which is the derivative. All right, so the derivative of the sine of 6x is the cosine of 6x times the derivative of the inside, so times 6. And then the derivative of the bottom, the derivative of tangent is secant squared. Leave the inside alone. And then times the derivative of the inside, 2. All right, so let's simplify that. So that's 6, limit as x goes to 0, 6 cosine of 6x, and then 2 secant squared 2x. So now we can plug in 0.
Is it fine if you simplify to 3 cosine 6x over
Yes.
secant squared?
Yeah. Yep, we can cancel that 6 and 2 and make that a 3. That's fine.
Right.
Okay. All right, so we're plugging in 0 first off. So both of those are going to be the cosine of 0 and secant squared of 0, right? So we're plugging in 0 for x. So yeah, we can make that a 3. So let's go ahead and do that. So 3 cosine of 0, 6 times 0, over the secant squared of 0. And the cosine of 0 is 1. And the secant is the reciprocal of cosine. So that would also be 1 over 1. So we're going to do 3 times 1 over 1. 1 squared is 1. Okay, so we end up with 3. Yes?
How'd you do the secant squared?
Okay, so remember the cosine of 0 is 1, right? So we're over here at 0, so that ordered pair is 1, 0, right? So the cosine is 1. The secant is the reciprocal of the cosine. So the reciprocal of 1 would be 1 over 1. So the secant is also 1, and then you're squaring it. So 1 squared is just 1. Does that make sense? So secant squared of 0, right? So that's really the secant of 0 squared. And the secant of 0 is 1, because it's the reciprocal of 1. So you're just squaring that. Okay? Yeah, secants are reciprocal of cosine. Now, if I asked you for the cosecant, that would be undefined, because 1 over 0 I couldn't do. But I can do the secant here. 1 over 1 is just 1. Okay? All right. So that one, again, trig functions. You guys still, they throw those in there every now and then. Be careful with this. All right. Number 16. This is a natural log. Okay, so again, remember that picture I drew before. So if we're going to 0 from the right, that natural log is going to negative infinity. And if I put 0 in here, 0 to the 4th is 0. So this is a 0 times infinity problem. So that means I can use L'Hopital's rule. And it doesn't matter if you do 0 times infinity or negative infinity. Any type of infinity is fine. Okay, so again, if I'm looking at this problem, some of you might say, well, the natural log seems easier to put in the bottom. Don't ever put natural logs in the bottom, because your exponents are going to get bigger and bigger down there. So we're going to choose the x to the 4th and put that in the bottom. All right, so we're going to do the limit as x goes to 0 from the right. Leave the natural log in the top, and then in the bottom you're going to put 1 over x to the 4th. So we've made a fraction, and that, again, is the whole point. and then simplify the fraction. Before you take derivatives, see if you can write the bottom a better way. So how can you write a better way 1 over x to the 4th? X to the negative 4, right? Okay. And so that's why I said earlier, I'm going through this with you and I'm doing what the rule says, but most of you, once you start doing this, will see, oh, if I'm putting x to the 4th in the bottom, it's just x to the negative 4, and you can skip this as long as you see it. But I want to show you because some of you need to see it. Okay? So it's always 1 over the function and then simplify that if you can. All right, so now we're ready to do L'Hopital's rule. Okay, so derivatives of the top, derivatives of the bottom. So I got my fraction now. All right, so the derivative of the natural log, 1 over x in the top. And then the derivative of x to the negative 4 is negative 4x to the negative 5, right? Okay, now I got to simplify that. I don't want to put in 0 yet because if I look at that, it looks like I'm going to still get zeros over 0, and that's not true. So this is the first time where we need to simplify a little bit our limit over there. All right, so do we agree? I'm going to do this kind of in a few steps. I'm going to leave 1 over x for a minute in the top. And I want to rewrite negative 4x to the negative 5 without that negative exponent, so you can see how to simplify this. So that would be negative 4 over x to the 5th, right? Mm-hmm. Because now I can flip and I can multiply by the reciprocal. And now your x's are going to be where they need to be. So if I were to simplify that, the limit as x goes to 0 from the right is 1 over x times, and we're going to flip this, right? So x to the 5th over negative 4. So that will simplify. After all this work, it's going to be a pain, but we can still simplify it. We're going to get an answer. All right, so this x is going to cancel with one of those x's. So that's x to the 4th in the top over negative 4. Oop, forgot my limit. Okay. So the limit as x goes to 0 of x to the 4th over negative 4. So I can plug 0 in here. Right? So I'm going to get 0 over negative 4, which is 0. It's a lot of work to get 0. But what I'm wanting you to see is if you tried to put 0 in here, a lot of you would say, oh, 1 over 0, that's 0, and then if I put 0 in here, 0. So I'm getting 0 over 0, and then you would keep going, and that's not true. So anytime you have something that looks kind of nasty, simplify it, because a lot of times when you simplify it, you can actually work the problem, okay? So always look at that. So if I got multiple x's in the problem, I want to simplify it down before I plug it in, okay? Because otherwise it looks like you have to continue and you don't. Good? All right, one more of these and then we'll look at, we've got 2 other types to do. All right, so this last one, x to the 5th times e to the negative x to the 4th. All right, so check and make sure you have the right form. So infinity to the 5th is infinity. And then e to the really big number, negative really big number, will be 0, right? So we're getting 1 over a really big number since it's a negative exponent. So e to the negative infinity is going to be a really, really small number. All right, so which of these do you think you'd want to put at the bottom?
E.
I would choose the e because when you take the e and put it in the bottom, it's going to be a positive x to the 4th. If you take the x to the 5th and put it in the bottom, it's going to become x to the negative 5, and then you have more negatives to deal with. So I think I'm going to put the e in the bottom. So let's see how that looks. Okay, so the limit as x goes to infinity. So leave the x to the 5th. Now again, I'm going to write it the way that the problem says, and then I'll fix it. You don't have to do this first step if you got it. So it's 1 over e to the negative x to the 4th. But that's going to simplify to x to the 5th over e to the x to the 4th. Okay, so we lose that negative sign. All right, so that's what we want to work with. Now, I will tell you, because it happens every now and then, typically, no matter what you put in the bottom, you'll get an answer. You can do it. Sometimes it's harder, but there's a few cases where if you pick the wrong thing and put it in the bottom, like the natural log, that's one of those cases. When you do your derivatives, the exponents keep getting bigger and bigger, and so then if, let's say, you're plugging in, zeros or infinity, you're still going to get that same, you'll be in a cycle and you will never get out of it. If you try L'Hopital's rule 4 or 5 times and you're not getting anywhere, then stop and try the problem the other way. Put the other thing in the bottom, because that's typically what will happen, okay? So some of the problems, and I know there's one on the appendix worksheet like that. You have to do it a specific way. So I always say, after you've done L'Hopital's rule 3 times and you're still not getting anything, go back to the beginning of the problem and flip it around the other way, okay? All right, so let's look at this one. So we're going to do derivative. So this is my L'Hopital rule part. So the derivative of the top is 5x to the 4th. All right, now the bottom, derivative of e to the anything is e to the anything, and then times the derivative of the exponent. So that would be 4x cubed. And simplify this. Before you plug in infinity, simplify. Okay? So I can cancel the x cubed over here with 3 of those, right?
Yeah, so 5.
So this thing is going to be 5x over e, 4, I'll put the 4 out front, 4e to the x to the 4th. So I canceled these x cubes in the bottom with 3 of those, right? Nothing else can simplify. Well, if I plug in infinity, a really large number, 5 times infinity is infinity, and 4e to a really big number is infinity. So I still have infinity over infinity, so I have to do L'Hopital's rule again. Remember, infinity over infinity is a indeterminate form for these. Okay? So I'm going to put, I got infinity over infinity right there. So that means I'm going to do another derivative. Okay? So the limit as x goes to infinity this time, and I'll lose the x in the top, which is what I need. So the derivative of 5x is 5. The derivative of 4e to the x to the 4th is 4e x to the 4th times the derivative of the exponent again, 4x cubed. But that doesn't matter, because now I don't even have to simplify that. Well, I really can't, other than making it 16 in the bottom. So if I plug infinity to the top, I'm going to get 5. And what are you going to get if you plug in a really big number in the bottom? Really big number, right?
So
So what is 5 over really big numbers?
0.
Okay, 0. Okay, right? So if I plug in infinity in the bottom, you could simplify it, but the only thing to simplify the bottom would make that 16 e to the x to the 4th x cubed, so I didn't feel like doing it. Okay. All right, but you can tell if you put in a big number in the bottom, that whole bottom's going to get bigger and bigger. Okay. All right, so that's the multiplication problems turned into division so that we can use L'Hopital's rule. Okay? So, and typically on your final exam, like on our test, it'll say use L'Hopital's rule because that's what we're doing. But on the final exam, it's just going to say final limits. It's not going to tell you which way to do it. So, back to the chapter 1, any of those, and some of you were actually doing that because you already knew L'Hopital's rule. So on the final, you can do it any way you want to. Okay, so just kind of remember all your different methods. Okay, I'm only going to do one of the subtraction. So I got to take a subtraction problem and turn it into division. Okay, so we pretty much any kind of problem in math, you can turn it into a division problem. So if you have a subtraction problem, first and foremost, it has to be infinity minus infinity. Okay, so if you're given a limit problem that is starting with subtraction, and you check, you have to get infinity over infinity. And remember what I told you, cosecant and cotangent have asymptotes at 0. So the cosecant of 0 minus the cotangent of 0 is some form of infinity. I don't care if it's negative or positive, but this is going to end up being infinity minus infinity, because those are both asymptotes. So that's the first thing. Typically, you wouldn't be given a subtraction problem if you couldn't do it in this section. So how do we make it a division problem? Okay. All right, so there's only two ways to do that. You can either factor, which I can't factor anything out of here, or I could use fractions. And in this case, I can use fractions because both cosecant and cotangent can be written in the fraction form. So let's see what that looks like. So the limit as x goes to 0. Cosecant is reciprocal of what?
Secant.
1 over what?
1 over sine.
1 over the sine. It is secant, but that wouldn't be, we want to try to get these to be the same. So yeah, you could do that. I don't want to say no to that one. All right, and then cotangent is 1 over tangent, but I don't want tangent in the bottom. I'm trying to get common denominator. So cotangent is also cosine over sine.
Yeah.
That's why I chose the sine for the first one. Okay. All right, so notice, now that I wrote these as fractions, I can get a common denominator, and luckily this one already has a common denominator. But once you get your common denominator, you've now got a quotient, okay? So this is equal to the limit as x goes to 0 of 1 minus the cosine of ax over the sine of ax, and look, just like that, we got our fraction. Now, I just want to mention factoring to you, because I don't have one of these on here. But if you factored, like, let's say I had another, like, 4x out front or something, and you factored out the 4x, well, then you've turned your subtraction into a multiplication problem, right? The 4x times whatever's left. And then you could take the 4x and put it as 1 over in the bottom, just like we just finished. So the factoring ones are typically just like the ones we just did. So once you factor out something, then that goes in the bottom doing the 1 over, okay? So I think there's one on the appendix pages like that, so. All right, so now we're going to do L'Hopital's rule. We're going to do our derivatives, so let's see what we get. All right, so 1 is gone, derivative of 1, 0. This is negative cosine. So the derivative of negative cosine is going to change that to negative sine, so that's going to be positive, right? So sine of ax times the derivative of the inside, which is a. And then the derivative of the sine of ax in the bottom, cosine of ax times the derivative of the inside. All right, and if we put 0 in, so we got a times 0, which is 0, and a times 0 in the bottom. So we have, plugging in 0, the sine of 0 times a over the cosine of 0 times a. And this will give us an answer, because the sine of 0 is 0, but the cosine of 0 is 1. So we get 0 divided by a number, a, which is 0. 0 divided by anything is 0.
What happened to the 1 in front of the cosine?
It got taken out by the derivative.
This one?
Okay.
Yeah, derivative of 1 is 0, so I don't need that. Yep, and then it was negative, so instead of having a negative sign, I made that positive.
Okay.
Okay? All right, so that's the subtraction one. You don't get a whole lot of those, so. And now the fun ones. So the next last three, are using our most fun different logarithmic differentiation. We need natural logs for these. Okay, so 19 is the easier one. Actually, 21 is probably easier than 20. They're probably in the wrong order, but so some are not too bad. There's a whole lot of stuff going on in the directions. I don't know if that's helpful to you or not. So this last part is when you have, again, the x, the variable x in the base, and there's a variable x in the exponent. Always, if I see that, no matter what I'm doing, I have to use logarithmic differentiation. So on the right, up there in your little steps, kind of tells you what you have to do. It's really a combination of everything we've just done, except for that natural log part, okay? So what we're going to do, since I have to get that variable x out of the exponent, the only way I can do it is to do a natural log. And if I do a natural log, then I can bring the exponent out front. Once I bring the exponent out front, guess what? I have a multiplication problem. And then I can take that number and put it in 1 over the bottom, just like we've been doing. So it's very similar. It's just that I can't just take the natural log. That changes the whole problem. So I have to take the natural log of both sides. And usually when you have a limit problem, you don't see both sides. So the very first thing it tells you up there is write this, because remember, the limit is the y value, right? And that's what we're looking for. So the first thing they ask you to do is just write it as y equals this. Now I got two parts, and I got two sides. Okay, so every problem has two sides. It's just we haven't been working with the y equals part because we've been getting answers. Okay, so that's what it says up at the top. First thing you're going to do is write it as y equals. All right, now, for your L'Hopital rule, you're allowed to check and get 0 over 0, infinity over 0, or 1 to the infinity. Again, typically in this section, if you're given a problem like that, it will be one of those three forms. So if I plug in 0 here, this one is in the form 0 to the 0, right? So x is 0. So again, you want to check, and you're allowed to get any one of these three forms. And that means you can do L'Hopital's rule. All right, so then it says take the natural log of both sides. So I'm going to do the natural log of y equals, and then remember, we're going to keep the natural log with the function. Don't put the natural log out front. So this is going to be the limit as x goes to 0 from the right of the natural log of x to the x. You always want to keep, remember, limits can work nicely that way. All right, now here's the thing. As soon as you do that, hopefully that's your reminder that when you get your answer, you're going to have to do something with it, okay? Can't forget about that natural log over there. So I always put a little arrow, squiggly line, because that means, because a lot of you, as I understand, we're going to have a lot to do by the next test. You work this out and you get your answer just like we got it up here, and you circle it. And if you do that, that is wrong. You got to do something with this answer, okay? So this little squiggly line hopefully will remind you you're not done. You got to do something. All right, so for now we're going to work on the right-hand side. So I'm going to bring the exponent out front. That's why I took the natural log. So this is x times the natural log of x. And look at, like I just got a multiplication problem. And now it's just like what we did on the page before. We're going to pick one of those two functions and put it in the bottom.
Never put that one.
And I don't want to use the natural log in the bottom. So that means I have no choice but to put the x in the bottom. So I'm going to rewrite this as the limit as x goes to 0 from the right as the natural log of x over 1 over x. Remember, you put it in the bottom, 1 over. And then before you take the derivative, go ahead and simplify the bottom to x to the negative 1. It's just easier to do that when you're doing your derivatives. So this is the natural log of x over x to the negative 1. All right. So now we're ready to do L'Hopital's rule. It's the only step, LH, right there. We're getting ready to do the derivatives. So the limit as x goes to 0 from the right. So the derivative of natural log is 1 over x over derivative of x to the negative 1, negative 1, x to the negative 2. All right, now this is that one where you have to simplify. So remember what we did in that other problem. So let's rewrite the bottom as negative 1 over x squared, and then we're going to flip it and multiply. And I do these steps, I mean, we should be able to do that in our head, but some of you get lost where the x's go. So just take your time and do the steps. It's not a big deal. All right, so the limit as x goes to 0 from the right of 1 over x over negative 1 over x squared. And hopefully that way you can see that you're going to flip and multiply the denominator, and then you can simplify it. Okay? Everybody with me? So I just changed the negative 1 over negative 1x to the negative 2, changed it to negative 1 over x squared. So now that gives me the limit of 1 over x times, and then you're going to flip the bottom, so x squared over negative 1. So what does that give us?
X squared over negative x.
So that's the limit of negative x, right? You know what you get? Negative x?
Mhm.
Everybody okay with that? So just take your time and simplify it. All right, so if you get negative x and you're plugging in getting really close to 0, you're going to get really close to 0. So the limit of that is 0, right? So you're not going to circle that. That's not your answer. The natural log of y equals 0. So you have to take your answer, okay, and put it back over here. So that has to come back over here. Now we can finish the problem. So I'm going to go back up to the directions now. The directions say, okay, you must set equal the natural log of y to what you found, and then change to exponential form. All right, the good news is it's the same thing. So how do I write this as in exponential form? What's the base? E to the 0 equals, and you're done. You're solved for y. There's your answer, e to the 0, which is what? 1. Okay. So you're solving for y. You're not solving for the limit. Okay, you're solving for y. And so basically, I always tell you guys this, basically your answer is e to this number. That's always what it's going to be. Okay, your answer will always be e to whatever you just got over there. Because every time you rewrite it in exponential form, you're going to get e to that number, and that will be your answer. Okay, so just don't forget to do that. It's very easy to forget that piece. And you know what? If it's multiple choice, guess what you're going to see on one of your answers? You're going to see that answer there. So don't circle it. Some of you go too fast and you forget that. All right, now this one, well, these two, a little bit harder, but same steps. So don't, and again, just do the steps. Okay, a lot of you like to rush through and skip steps. It's too many exponents, too many negative signs. So just take your time with it. All right, so first off, check it. We're putting in infinity. Okay, so 1 plus 2 over a really big number, that means 2 over the real big number would be 0. So in here, you're going to have 1. And then 3 times a really big number is infinity. So this one is of the form 1 to the infinity, which is one of the 3. So I can do that. Yes?
I have a question. So, like, it was saying that 1 to the infinity, you can never tell if it's just going to be 1, but isn't 1 to any number 1? I didn't really understand that.
Yeah.
Well, it's, yeah, that's true, but in this case, since we're doing limits and we're getting close to those numbers, we can't, these are really going to have values.
Okay.
It will be a number close to that, but yeah,
Okay.
it's not going to be exactly that.
Okay, thank you.
Okay? Well, and actually, this one won't be really close to that, I don't think. So yeah, that's not true. I take that back. So yeah, you can't just assume that, okay? All right. I'll have to look into that, see why that is. I'll get back to you on that one. All right, so we're going to rewrite this as y equals. Remember, we're going to put the natural log in there. So let's do that first. All right. So since I have that form, we can stick that y out there. All right, so we're going to do the natural log of both sides, and remember to keep the natural log with the function. And again, a lot of these, you guys can kind of combine these steps. I'm just doing it so we can see it and have it. All right, so this comes down. So I know I'm going to have to do something with my answer. Okay? The biggest thing on this is that you just don't write what you get. All right, so we're going to take the 3x and we're going to bring it out front since I have that natural log. So this is the limit as x goes to infinity. 3x times the natural log of 1 plus 2 over x. Okay. Now, 3 is a constant, and I will put a little note, whatever you have to do. When you move a function to the bottom, don't take a constant with you. okay? Because if I take the 3x and put it in the bottom, some of you are going to run into some big problems on where that 3 or that number is going to go in your answer. So think about that. If I just put the x in the bottom and leave the 3 with this natural log, it's the same problem, right? So leave constants. Leave constants in the numerator. Only move the variable part to the bottom, okay? So I'm going to rewrite this as the limit, as x goes to infinity, of 3 natural log 1 plus 2 over x, and then I'm putting in the bottom just the x, so 1 over x in the bottom. Okay. Constants don't need to go with the variable. You could, and it's fine to put 1 over 3x. But the problem with that is if you simplify 1 over 3x, a lot of you will tell me that's 3x to the negative 1, and it is not. It is 1/3 x to the negative 1, and you've already screwed up your problem because you put the 3 in the wrong place. So by leaving it in the top, you don't have that problem, okay? All right, so let's rewrite this as x to the negative 1 before we do our derivatives. So, as always, we're just going to fix the bottom. So this one looks bad, but it really will fix itself. So, all right, so that's what we're going to take the derivative of. So we got 3 natural log, 1 plus 2 over x in the top, and then I changed the 1 over x to just x to the negative 1 in the denominator, so it'll be easier to take the derivative of it. So I've done no L'Hopital's rule yet. I've just been simplifying. So now I'm ready to do the L'Hopital rule step, the derivative part. Okay, so limit x goes to infinity. All right, now, let's take your time with the top. Okay, we're going to take the derivative of the top. So the 3 is going to stay there. It's constant. Times derivative of any natural log is 1 over whatever's here, right? So 1 over this whole thing. Okay. Times the derivative of the inside. So what is the derivative of the inside?
Negative 2x to the negative 2.
Okay, think about that. Derivative of 1 is 0, but this is 2x to the negative 1, right? So what is the derivative of 2x to the negative 1? That's negative 2x to the negative 2. All right, don't forget that. So I'll say that again. Look at the top. Make sure we're okay. So 3 stays. The derivative of natural log is always 1 over whatever you're taking the natural log of, so that's that part. And then times the derivative of the inside, right? Okay, over, and here's what's nice about it. Look what happens. What's the derivative in the bottom?
Minus x.
Negative 1, x to the negative 2, right?
Okay.
So we're going to simplify. So these x to the negative 2s are going to go away. You got a negative divided by a negative, which is going to make that positive. And then you have 2 times 3, which is 6. So we have, excuse me, the limit as x goes to infinity of 6 over 1 plus 2 over x. That's not so bad. Okay, so I put the 3 times 2 is 6. That was in the numerator. And then this is still in the bottom. So 6 over 1 plus 2 over x, and x is going to infinity. So what's happening to the 2 over x? I'm going to substitute in my numbers. So that's 2 over a really big number, 0, right? So I have 6 over 1 plus 0, which is 6. Right with me? All right, plugging in infinity for x. So 2 over, remember, anything that still has the x in it goes to 0 when you're going to infinity. All right, so is my answer 6? Nope, right?
No.
What are we doing with that? We're taking it and putting it right here. So the natural log of y equals 6, so that means e to the 6th is y. That's your answer. You can leave it like that. Or you can do e to the 6th power, which is not close to 1. That's why I said that. All right, so e to the 6th. So you could write 403.4. So that didn't work. So no, it's not going to be 1. All right, but e to the 6 is fine. WebWorks likes e to the 6. If you're going to put the 403 number in, make sure you put enough numbers after the decimal point. Okay? All right, so we're going to do one more like that. And actually, 21's a little bit easier, except for that negative sign. You got to watch your minus sign here. That's probably the biggest part of this one. Okay? All right, so we okay with 20? All right, so looking at this one, x goes to 0. Okay? So do I have the right form? So if I let x go to 0, in the parentheses, I have 1 minus 7 times 0, so that's 1. And then 1 over really small numbers are really big numbers, right? 1 over 0.1, 1 over 0.2, so 1 over, so that's your infinity. So that is the right form. So we're going to do y equals, it's okay if I put the natural log in that step. Okay, so natural log of y equals the limit x goes to 0, natural log 1 minus 7x. Okay, so I'm just kind of combining those first two steps. So y equals, and then take the natural log of both sides. All right, so the rules are the same. That's the nice thing about this logarithmic differentiation. Can't really, once you have it, there's nothing different that happens in any problem. All right, so let's bring the exponent out front. So this one's kind of interesting. When you bring the exponent out front, which is 1 over x, think about how that goes in the denominator.
Over x.
You got 1 over x. So what is that going to give you in the bottom?
X.
Just x, right? So when we switch it, I'm going to leave the natural log in the top. And 1 over x is just x. So when you put that in the bottom, it becomes x. It's actually already in the bottom. Think about it, right? If I just asked you to simplify this, wouldn't you write natural log of 1 minus 7 over x? So it already is a fraction. So I'm just rewriting it. Okay, so now we're ready to do L'Hopital. So let's see what we get. All right. So derivative of natural log in the top is 1 over whatever you're taking the natural log of times the derivative of the inside. Negative 7 over derivative of the bottom is just 1. Okay, so that simplifies to negative 7 over 1 minus 7x. And x is going to 0. So when we substitute that in, we get negative 7 over 1. Okay. 7 times 0 is 0. So negative 7. So you got to watch that sign. So your natural log, remember you're putting that into here. So negative 7 is not your answer. Your answer is e to the negative 7. Okay, that's fine to leave it like that. If you do e to that, you get scientific notation, so 0.00091-ish. Okay. If you plug it in your calculator, I'm just going to stick this up here. I think we've done these before, but right? You get scientific notation. Remember that means move the decimal point 4 places to the left. Okay? But you can leave it written as e if you want.